Le Chatelier's principle says that if a system is at equilibrium and that system is then stressed, that reaction will shift against the stress in order to reestablish that equilibrium, which is really just a fancy way of saying as long as the system's already at equilibrium, if you do something to disrupt that equilibrium, the system will work its way back, undoing whatever stress you applied to it to make sure the equilibrium is reestablished. It is important to note, though, that any of these stresses that you cause on the system do not change the value of K. So your value of your K, your equilibrium constant, does not change simply due to these stresses. So let's go through what some of these stresses could be. The first one is the addition of a substance. Well, to help us get a more visual picture of this, let's draw a graph here. And on the x-axis, let's label it time. And the y-axis we'll label concentration. Okay, and let's say we have a reaction that's going to establish equilibrium where A is reversible to make B. Okay, and we'll just decide that the amount of A we start with happens to correspond to this line right here. So what that means is that A will decrease in concentration as this works towards equilibrium because the reaction has to produce some products. So A will decrease, but you should see the sharpest decrease at the beginning, and then the reaction should level off at equilibrium. Well, B must start at 0 because there isn't any B at the beginning of this, but it should also appear rapidly in the beginning and then level off wherever A leveled off. So we could label a few points here. This first point right here is the establishment of equilibrium because the concentrations of A and B stop changing. Let me get those off there. Okay, but now I want to imagine that we are going to introduce some more A. Let's consider the addition of reactants. So the system is at equilibrium, and then just out of nowhere, we add some more A, some more of this reactant to the system. Well, graphically, what that's going to look like is it's going to look like just this sharp, straight vertical increase here because the concentration of A was here, and then you put some more in, so now the concentration is much higher. Well, that addition has disrupted this equilibrium. You've put a stress on this equilibrium system, so this system's going to move to offset that. Right now, there's more A than there should have been according to where this equilibrium fell. So for that reason, the additions of reactants causes the system to favor the forward reaction. So this causes the forward reaction to be favored. So if this forward reaction is favored, that means this reaction is going to progress to the right, meaning some of this newly added A has to turn into B. So what you'll see is that A drops again before ultimately leveling off. Now it's important to note here that whatever this concentration was before, you are not going to hit it again. You're simply reestablishing equilibrium. That doesn't mean you're getting your concentrations back to where they were. In fact, you can't because you added more A, so that's not a possibility. But down here on our B, the opposite's going to happen. As this A was consumed, it was turning into B, so this concentration of B has to increase and again establish a new equilibrium. So again, where these level off, you have equilibrium being reestablished. Equilibrium being reestablished. Okay? Now you can imagine this in the reverse direction. Let me clear this out. What if instead of adding reactants, there was an addition of products? Well, that means now I've disrupted the equilibrium, but I've increased the concentration of B here. So the vertical increase will be right here on B, but now there's too much B. So this reaction is going to work to use up that B, which means the addition of these products causes the reverse reaction to be favored. So graphically, let's think what that means. There's too much B in this case. Some of that B is going to have to be consumed in order to reestablish its equilibrium. But since that B is being consumed and it's turning back into A, then we should see the concentration of A increase and ultimately level off again reestablishing a new equilibrium. If we consider removing a substance instead, let's draw another similar graph here. Again, our x-axis will be time, our y-axis can be concentration. Concentration. And let's stick with the same reaction where A is reversible to make B. We know A began and leveled out, and B began at 0 and leveled out. I drew those a little too long. Let's erase those. There we go. Okay. Now let's think about what removing a reactant would do. Removing reactant. Well, think about this. Instead of our vertical piece being going up, our vertical piece here would be going down. So our concentration of A is going to dramatically drop. The system was already at equilibrium, and then we siphon off some reactant. Well, now there's not enough A as there should have been at equilibrium. This reaction will work to undo the stress applied to it, which means it's going to replenish A, but it's going to replenish A at the expense of B. So while this A will slowly creep its way back up, trying to reestablish equilibrium, this B would have to decrease to offset that. The only way to end up getting more A is at the expense of B. So removing reactants, removing a reactant favors the reverse reaction, because the removal of those reactants forces the reaction to produce more of those reactants, which is going in the backwards direction. The opposite is true if you remove products. So removing products must then favor the forward reaction. Let's clear this graph out. Let's think about what that would look like. This is probably the most real-world applicable portion of this, because let's say I'm a manufacturing company and my job is to produce B to sell to, maybe it's fertilizer we're selling to a farm or something. If I'm trying to produce as much B as possible, then I want this reaction to constantly be moving towards B. I don't want equilibrium to stop my reaction. Well, if I continuously siphon off this B, then this reaction will continuously work to reproduce B, which gives me basically an unlimited supply of B because I never let the reaction settle. But let's think about what that looks like if I do let the reaction settle. I just take away some B at the beginning. So B will have a sharp decrease as I remove that B, but the reaction is going to work to replenish it, so I should see an increase in B. Again, it will never get back to where it was, but it will work towards there. In order to make more B, that comes at the expense of A, so more A should decrease. I should see another dip in A. And again, we have a new establishment of equilibrium here as the reaction has worked to undo the stress that we caused to it. Another stress is the changing of the pressure. Well, if you think logically here, this would only apply to gases. And we typically would consider changing the pressure by changing the volume. Okay, so again, Le Chatelier's principle says we're going to work against whatever stress is caused here. So these next parts, it's a little bit logical, but it takes some seeing to kind of imagine it. Increasing the pressure. So let's say I decrease the volume of my container, that increases the pressure. This system is going to work to offset that increase of pressure. So one way to offset an increase in pressure is to have fewer gaseous particles. So increasing the pressure actually favors the side of the reaction with fewer gaseous, fewer moles of gas. Let's word it that way. With fewer moles of gas. Well, before we try to look at an example, let's go ahead and just state the opposite of this. If I'm decreasing the pressure, so maybe I increase the volume, which would decrease the pressure here. Decreasing the pressure favors the side with more moles of gas. And that's logical if you think about it. I'm trying to offset a decrease. How can I offset a decrease? Make more moles of a gas. Well, let's consider what this looks like with an actual reaction. We'll get some of this out of the way. And again, let's consider, we'll switch up a little bit. 2A, which is a gas, is reversible to make B, which is a gas. So the first thing I want to point out is that there is 1 mole, no there's not. There's 2 moles of gas on the reactant side, but there's only 1 mole of gas on the product side. So if I were to increase the pressure here, if I increase the pressure of this sample, this reaction is going to shift to the side with fewer gas particles. It doesn't matter whether they're on the reactant side or the product side. I'm simply going to move to the side that has fewer particles. In this case, that would shift my reaction towards the forward, in the forward direction towards B, because there's fewer particles. So an increase of this particular system would result in the forward reaction being favored. But if I decrease the pressure, that's going to favor the side with more moles, because more moles of gaseous particles will offset a decrease in pressure. So a decrease in pressure will favor the reverse reaction. Well, then the last way that we can stress a reaction is with changing the temperature. In order to help us think about this a little bit better, though, I want to write out something a little bit differently than maybe you've seen it, or maybe this is the way you've seen it. I don't know. A is reversible to make B, but heat is also a product. Or, let's say A is reversible, let me undo that. A plus heat is reversible to make B. So with this, heat is produced here. Heat is being released. So you can consider this to be a way to write an exothermic process. This would be exothermic. Your delta H would be less than 0. It's exothermic. Here, heat is being absorbed into the reaction. You can think of it that way. So this would be endothermic. This delta H would be positive, greater than 0. Okay, so the easiest way to think about how this temperature changes is by kind of thinking about heat as either a product or a reactant. Let's make a chart. We'll have 3 columns. On this one, we'll say endo or exothermic. On this middle column, we'll have a temperature change. Remember, delta triangle means change. And on this column, we'll have the favored direction. And this chart's easier than having to list out so many sentences. We'll just think about it this way. Let's say that the reaction is endothermic. Okay? So that's this section right here. Heat is being consumed like a reactant. And let's say for this one, we increase the temperature of the system. Well, I want you to treat this just like it was the addition of a substance here. The addition of a reactant causes the forward reaction to be favored, right here, but the addition of a product causes the reverse reaction to be favored. So let's bounce back. In an endothermic process, you can think of heat as a reactant. So I'm increasing the heat, which means I'm increasing a reactant in essence. That's going to drive this to be forward favored in order to quote unquote offset that heat that is being added. Well, let's say the reaction's endothermic, but I decrease the temperature. Well, now that's like removing a substance. This heat is still being treated as a reactant, but now I'm removing it. That's going to cause the reaction to progress backwards to offset that removal of heat. So decreasing the temperature of an endothermic process will favor the reverse reaction. Well, now let's jump to an exothermic reaction, and let's say we're increasing the temperature of it. Okay, in an exothermic process, heat is being produced, it's being released, it's a product, however you want to word that, and I'm increasing the amount of heat by increasing the temperature. Well, that's going to push this reaction backwards in order to offset that addition of the heat. So an exothermic process where the temperature is increased will favor the reverse reaction. So then it stands good reason that an exothermic process in which the temperature is decreased should favor the forward reaction. But let's take a look and make sure that makes sense. In an exothermic process, heat is a product. I am, quote unquote, taking away heat when I decrease that temperature, which should force this reaction forward to replenish that heat. So indeed, it is a forward process. So these are just some of the stresses that you'll be expected to analyze when you're talking about Le Chatelier's principle and how they impact the favorability of the forward or reverse reaction.